Okay. I'd also like to thank the organizer for a nice invitation. And the title is DFT as a pathway to quantum string. And this, I believe, is a higher spin section. But I'm not going to talk about higher spin theory that I've been working on actively recently, partly because last week I gave a talk in just a couple of blocks away about this partially massless Higgs mechanism. And also I talked about Carl of higher spin gravity, which I'm very excited about, in several recent higher spin workshops. So you can find them on the web pages. Rather, I'd like to take this as an advantage for me as an opportunity to share some thought on something very explorative and wild. And I'm very glad that I'm not the first one in this 5-day conference. There were several people already. So let me move on. So there are some works I've been doing, and this is mostly based on this work in progress right now, in collaboration with excellent people in my group, as well as outside Japan and Argentina. And I was also very pleasant surprised that Arkani Hamed gave a very nice talk, which seemed to be along the same line of thought. And yesterday, in parallel session, Yutin Huang also gave a quite relevant and very nice talk. So say I have an excellent graduate student. I always have some. And he was always constantly bugging me. And I just wanted to expel him for a while so that I can finish my own project. So I gave this problem. So go back and calculate, see if this is calculable and predictable theory. And I thought that this will occupy him for a while so that I can finish my own. And it's a quite complicated Lagrangian, several coupling constant. And so I thought I will be very successful. And of course, I had a secret code why I gave this problem. If you look at this Lagrangian and stare at a couple of lines, you notice that every single term has two derivatives. And my secret code is Einstein gravity. When you expand around whatever background, flat background or ADS, whatever, it again has two derivatives in every single vertex. And if you count the superficial degree of divergence at loop, it just depends on number of loops, and it's totally independent of number of external legs. Very different from conventional field theories we know, and that's the reason why the theory is non-renormalizable. And the student was so smart, he came back to us next morning and said the theory is trivial. And indeed it is. The reason is, if you make canonical transformation field variable from what I gave in the 2 pages above, if you make this change of variable to capital phi and capital psi in that way, that whole Lagrangian, this one collapses down to this middle line, the two decoupled free field theory. So I was frustrated. So I insisted on checking again, going back to this one in this Lagrangian. Don't wave your hand. Still compute something to support why this Lagrangian is free. And lo and behold, and he came back again. And this is sort of Slavnov-Taylor-like identity. If you look at this canonical change of variable, and each term by term might have each diagram-wise renormalization, but that renormalization has to satisfy certain relation, which is very restrictive. For example, if you look at the renormalization factors of each factor in the first line, and here phi and phi cube and psi 9, whatever, and if you look at this, the renormalization factor in each order by order, that ratio has to be the same. That's first one. Second one is the whole result has to collapse to 1. That's because final theory is a free theory. Okay? So this is the way, if you were clumsy enough to rediscover that the trick I gave to a student is discovered to be a free theory. Okay, so I gave a next problem. So that was too easy, so to a free field theory. So I decided to give us something related to the same sort of behavior, which is ON nonlinear sigma model for n-1 pions. And again, it has a two derivative for every single vertex, but again, it's a non-polynomial. And this theory is a non-trivial, it's an interacting theory. And I asked him to check whether the theory is predictable and is calculable, in other words, whether it's renormalizable. Of course it is not. This is a non-polynomial theory, even though this ON symmetry will constrain different vertices through world identities. This will generate infinitely many higher dimension operators, and we know this very well, that the theory is non-renormalizable. And in fact, if we look at this, the real process, like a three-level scattering process, we do know that this theory will have the partial wave unitarity violating at scale roughly around 4 pi f, where f is a scale sitting here. And also, if you compute the loop diagram, again, it's badly divergent and roughly at the virtuality above 4 pi f. So this theory is non-renormalizable. So I asked him, is there any way you can improve this one such that it has a better, softer UV behavior? And again, he came back with a nice answer. And then to do that, all you need to do is to introduce one more degrees of freedom, which is a Higgs field. And that's appending this n-1 pions as the magnitude direction, such that you have now linear sigma model of these quartic interactions whose the magnitude square is the Higgs field square. And this F scale coming into as the quadratic mass term, and it's nicely combined with this one, is such that when you have a strong coupling, it just reduces to the usual nonlinear sigma model. So this is the way we pave starting from non-renormalizable theory, which has a similar behavior as Einstein gravity, and marched up eventually to get into renormalizable theory, which is computable, therefore predictable. So let's take this as a metaphor. And before doing that, let's just take the maxima out of this student project. So to attain better high energy behavior and renormalizability and calculability, therefore predictability of a given theory, thing that we can learn from this exercise is first, you choose a variable smartly. If you did badly, you're not bad, but eventually it'll take a long time to figure out Slavnov-Taylor identities. Second, you introduce additional degrees of freedom in such a way high energy behavior becomes softer and better. And on top of that, precisely like this nonlinear sigma model, you might have gauge or global symmetries from non-linear realized phase into linear realized one. In other words, make it manifest so that helps the organization of UV behaviors. So this is the maxim. So let's bring this lesson to quantum theory of gravity. Now, nobody doubts that string theory is the theory behind quantum theory of gravity, but that's not the question I am asking. We have low energy Einstein gravity, and on top, in the heaven, we have string theory. In between, we want to understand the layer by layer, but the string theory, everybody to some degree or the other degrees, they all feel it's prohibitively complicated understanding the details. So the rule is usually we divide and conquer, and taking certain limit, for example, weak coupling or strong coupling by duality, or certain extreme kinematic asymptotics, or you massage the gauge symmetry into deformed form. So that is the rule of the game we've been playing around, and we'd like to do exercise along these directions in the case of the quantum theory of gravity. So we'd like to understand in what sense Einstein gravity, which is so bad, as the example I gave to students, is becoming better and better, eventually becomes a finite theory in the extreme UV by quantum string theory. So we start from a bottom up, we start from string Einstein gravity, and we take a pathway to string theory by taking all these different regimes, or maybe combination of that too. First one, very well known, we take a very low energy, below string tension scale, and we do have the massless supergravity multiplet, and we understand this dynamics very well. It's not much different from Einstein gravity, even though supergravity has a lot of surprises in recent computations of loop diagrams. Another corner is we take zero tension limit, or equivalently very high energy compared to string scale. Then we do have the enhanced or the restored gauge invariance, quote unquote, and higher spin gauge symmetry. And there we do have infinite number of infinite component field, but because of this gain in higher gauge symmetry, we believe we have a good handle of this regime in such a way that Einstein gravity better behaves than in this limit. But still, this is some corner of string theory. Now, in this talk, I want to take yet another limit. I will consider starting from Einstein gravity, which has its own gauge invariance, diffeomorphism invariance, and I will enlarge that gauge symmetry in a suitable way. And then embed, eventually they will go into the string theory. But my question is, by taking this, the intermediate step of the enlarged gauge symmetry with a finite number of component fields, how much do I gain insofar as the calculability or the predictability or the better high energy behavior is concerned? So that's the question I'd like to ask. By the way, I'd like to make one comment, which also might be related to earlier talk by Joel Komagowski, that here one of the limit is a higher spin theory. And in the context of the gravity, in gravity, well, there's a very nice argument by Maldacena, a very important observation that a causality constraint put necessitate that we should have in Einstein, that higher derivative gravity, a tower of massive higher spins. The immediate question is whether this massive infinite tower of higher spin is equivalent to the string theory. Is it the same thing? Or is there something in between? And rather than going details over this argument, I just, as a remark, I want to make one small point about this. If we consider ADS-D plus 1 Basilev theory, which is not string theory, but only higher spin of multiplicity 1 for each spin, and then compactify on ADS-D, and this was just discovered recently with my student, and in the background of so-called Janus genus, which has two boundaries, which was originally discovered by these people, then you can actually get a lower dimensional Vasilev theory, which has all massless higher spin, as well as infinite towers of a higher spin. And furthermore, there is no conserved Cauchy-Klein charges. Therefore, in this case, massive higher spin interacted with massless lower spin as well as spin 2 in the sense that this, the causality constraint analysis has been done. So if you look at the Shapiro time delay in ADS, the lower dimension, and then by this argument will necessitate all massive higher spin towers. However, in this theory, if you go to the very UV, then it simply goes into one originally back to ADS-D plus 1 Basilev theory, which is not quite string theory. So it's not yet going to the string, it's not instead higher spin theory rather than string theory. So the question I think is still needs to be understood better. Now, so let's take this roadmap, quote unquote, I call Higgs and Hunt. So as I said, I reiterate the question. I start Einstein gravity. We will eventually reach to the string theory. And on the way, we ask whether there is any sensible pathway where UV behavior becomes softer and better. And therefore, we can understand in what sense, quote unquote, this Higgs degrees of freedom improves the Einstein gravity towards string theory. It might be that it goes directly to the string theory, and there's nothing like Higgs, and that might be another lesson that we learn. So here, pathway, as I said, is taking the gauge symmetry, enlarge it. So Einstein gravity is the usual diffeomorphism, and string theory, even though we don't know what the full symmetry is, we do believe it's a huge symmetry. And in between, I will take as a proxy double field theory, which has a much larger symmetry than Einstein gravity, as a sort of proxy of the larger enlarged gauge symmetry in between diffeomorphism and string gauge symmetries. So the question is, if we enlarge diffeomorphism into this bigger one, therefore theory is far more constrained, then how is high energy behavior improved? And if so, how much is it? Now here, I want to make a disclaimer. I'm not going to advocate DFT as some fundamental theory or anything. I'm just taking this as a proxy for my maxim, namely, this is one concrete example that low energy gauge symmetry of Einstein gravity is enlarged on its way toward the string theory. So DFT, I just want to make a very brief the review, and it starts from T-dual symmetries. And we treat the momentum and winding quantum numbers on equal footing. So we introduce two coordinate, original coordinate, dual coordinate. And of course, this originally should be done on toroidal compactification, but I will just depart from that. I just take that symmetry as a more fundamental symmetries and view this is the guiding principle of enlarging the gauge symmetry. So the gauge symmetry is a diffeomorphism times this ODD, the duality symmetry. So starting from this d-dimensional physical space-time and it's a dual space-time, I go into 2D dimensional space-time, and turned out it has a signature plus d and minus d. And then eventually I also have to go back to the physical space-time, which is certain middle dimensional slice. And the way we achieve this one is so-called the section condition for any physical field in this theory. So likewise, all the fields, for example, massless mode in this case, G, B, and phi dilaton, has to be enlarged first and then subject to this section condition. And in this way, we sacrifice locality, but we manifest the diffeomorphism as well as ODD duality symmetry, which makes, by combining these two, the diffeomorphism symmetry is much large, enlarges much larger size, and that's basically the enlarged gauge invariance that I like to play around. So in the worldsheet language, world terminology, if I decompose my worldsheet coordinate into left moving and right moving, and the dual coordinate simply reflecting right moving coordinate, whereas keeping left moving, and this relative minus sign is precisely the origin of the OD comma D signature, as originally discovered by Kikawa and Yamazaki, as well as Narayan. And the section condition is nothing more than space-time picture of level matching condition for string field, which is L0 minus L0 by is to be 0. Again, this gauge, I'm just emphasize again the gauge symmetry by combining the ordinary diffeomorphism and ODD T duality became much bigger. So let's take that as a gauge symmetry. Okay. And I have this field, and then in this, we'd like to understand the dynamics of all this field in the weak field. This ODD, this double field theory in this terminology is much similar to weak field gravitational wave expansion in Einstein gravity. This is like a flat Minkowski metric, and there is the dynamical field, which is weak field, and its expectation value is denoted curly H. That's usual, for example, in toroidal compactification is a metric, and the B field and its inverse. And what the one constraint of this field, with a small fluctuating field, is that its square has to be 1, this one, the flat space metric. And this condition, along with this enlarged gauge symmetry, uniquely fixes the action, and action takes this form, and where R is the analog of Ricci scalar with respect to this enlarged diffeomorphism symmetry. And very interestingly, in terms of this field M, whose expectation value takes this kind of form, is only a finite polynomial and has only 2 derivatives. So this action is very nice, except one pitfall. One pitfall is that, unfortunately, this constraint M scale equals J, where M is fundamental field in this the double field theory of the gravity, has to be constrained to 1, much like nonlinear sigma model from the viewpoint of sigma model. And this makes, when we look at the small field expansion of this one, because of that, this corner, which I denote as G inverse, is related to G precisely by usual relation that if I expand G as 1 plus H, then G inverse as infinite polynomial, non-polynomial structure. So this is really bad. So the lesson is that this double field theory, even though it has enlarged gauge symmetry, at leading order in alpha prime, is no better than Einstein gravity. What about next order? You might think there's nothing you gain, but there's a surprise. So as I said, the metaphor from the student project is that I start from nonlinear theory, nonlinear sigma model, which is non-renormalizable, and try to go to a linear sigma model, which has much better UV behavior. And next order, this double field theory, I forgot to mention this nice computation by Holm and Siegel and Zwiebach, and they compute this one, and the structure is very nice in the sense that I have this leading term which was absent in the leading order, and then this first one is the usual 2 derivative term, and on top of it, because alpha prime corrections, I have 4 derivatives and 6 derivatives. And the details are not important. The important thing is that the derivative stops at finite order, and the number of fields, the powers of field also truncate at finite order. Most important thing is that this M, which was constrained to be M squared equal 1 at leading order alpha prime, is now off-shell. It can be any field. That means that in terms of original expressions of this H field or M field, this left corner block and right corner block doesn't need to be related by inverse relation. That means if I make a small field expansion in this field in the theory, then this one is just a finite polynomial, finite higher derivative field theory, and it has just a scalar potential like this one. As you can see in the leading order alpha prime, this one is the leading term whose saddle point equation is precisely M squared equal 1. So this is analog of linear sigma model or ON linear models. And so this is very, very nice and very unique, and there's no other possible constant you can write down which is consistent with this enlarged gauge symmetry. So this already suggests that this theory must have very nice quantum properties. So the question is, well, what are the analog of the Higgs mode which improves the high energy behavior? And what are also is high energy behavior really improved in what sense? So Higgs mode, if I look at these details of this one, then by expanding small field, what one finds is that at the level of occasional motion is this one. If I ignore these higher order corrections, then there are M and M bar field, and that M and M bar field are just auxiliary non-dynamical field, which just is related to small weak field metric and B field. And now with the alpha prime correction, it gets dynamics through this derivative term. Therefore, M and M bar are genuine dynamical field. So this alpha prime going zero limit is singular in the sense that leading order alpha prime, we have only GB phi supergravity field. But in the first order alpha prime, M and M bar kicks in as a new degrees of freedom. Furthermore, there's a side remark. This one is a very interesting model in the sense that I have ODD, the T-dual symmetry, which I can decompose into OD times OD. And all this field can be viewed as a equivalent matrix theory. For example, this M is a symmetric matrix, the representation of first OD and M by second one, and H is just by fundamental. And some similar structure was observed some time ago by Arkani Hamid and Kaplan. And this because of this structure, in fact, every diagram can be written in terms of this the large N gauge theoretic diagrams, except this is an unoriented diagram. And so I believe it has some potential application in taking large day limit of the gravity in the context of double field theory. For example, Strominger studied this one many decades ago, and recent work by Empran, and as we heard this week, Minwala, one might have some application in here. And indeed, the higher spin theory, as I first envisaged some time ago, was actually along this direction of enlarging the dimensions. Okay, I think I have to hurry up. And then Higgs mode is, okay, so if I look at this dynamics, and this, the equation of motion is very interesting. First of all, if I look at the kinetic term very carefully, it's not just a usual massive spin 2 field. Some of the components actually are non-dynamical, but it's not neither Lagrange multiplier. It's simply non-dynamical. Well, there's a bad curse kicking in. This M curly M field, or small m and m bar, which are dynamical, have a negative norm, much like a Pauli-Villar or its dynamical version Rietvik field. And the way, how do we understand this one, whether this is really bad or there's a way of understanding it, that's subject to discussion, and I will make some very speculative remark later. Next one is that it has mass square. One is usual mass, 4 over alpha prime, the other one is tachyonic. Now these masses are not random. This number could be something different depending on the unit, but however, this precise mass relation like this, as well as negative norm, are precisely needed first to get, after integrating out M and M bar, you get the usual leading order up double field theory action, and second, to get the structure of the dynamics in a compatible way with the double field theories. Now, the high energy behavior, I have to really hurry up, and we started several things. One thing is the 4-point amplitude, and compared to usual gravity, this, including this order alpha prime correction, gave certain corrections which gave soft behavior. In terms of KLT terminology, we have a usual open string-like diagram, which is first OD, and this is second OD, but remember that in the second OD we have minus sign here, and this the KLT kernel is now modified from usual 1 by this extra factor, and this extra factor improves the UV behavior. And in achieving this UV behavior, this mass relation as well as negative norm, this ghost-like behavior is very crucial. Second one, we also looked at the BCF factorization, and there's a nice way of understanding in terms of, intuitive way of understanding in terms of soft collinear scattering amplitude, and this symmetry of the spin, the Lorentz symmetry enhancement in that asymptotic kinematic regime is what governs the large Z behavior. And in this case, because M and M bar field, which is a ghost field, those cancels certain symmetry breaking, spin symmetry breaking terms of the pure Einstein gravity. Turned out that in this case, compared to usual behavior of the Einstein gravity, there is an additional suppression factor, like 1 over Z, precisely coming from this ghost field. Okay, finally, there's a vacuum amplitude. We can compute this one, and this is something surprising that we have usual field. This is a massless supergray field, and we have a ghost-like field, and there's a minus sign precise because of that. And there's this non-dynamical one, which you subtract out, as well as the time-like component of the M field. And if you add all them together, leading order lambda to the fourth cancels out. The lambda square is not, so therefore, this one is probably some coincidental thing. It reminds me of some the structural bosonic Yang-Mills theory in 26th dimension, which does not have leading UV divergences. So that's all about it, and so therefore the catchphrase is that double filter that at the first, or already in first order upper prime correction, that already has improved gravity, UV improved behavior as far as gravity is concerned. And so this is somewhat orthogonal, but it has similar directions to a high spin theory at higher loop order where you don't have any corrections from as gleaned from the conformal field theory. So let me just have just 30 seconds. And there's one very speculative remark I want to make. These are ghosts, so you might say this is a really bad theory. However, I just want to make this, the simple identity that if I have this usual field, the positive norm states of some mass m squared is not important. If you look at asymptotics large P, if I have infinite many fields of massless spin S with 2 degrees of freedom in 4 dimensions, for example, then I can just resum this one and I get 2 times zeta 0. That's just minus 1. So this one suggests that the infinite collection of higher spin, mass higher spin, asymptotic large p square limit, the effect of that might be effectively summarized by one negative ghost. I don't know whether this is a coincidence or this is something nonsense, but still I think it's interesting. And there are remarks I want to make in MB twister strings, and there are certain the recent activities which came across this relation, and double field theory achieves this from string theory to so-called chiral string in a very nice way, such that x and x tilde has this negative wrong sign in the holomorphic and anti-holomorphic sector. And I invite you to look at the transparency of Yutin Huang in the parallel session. And finally, this same kind of analysis can be done for little string theory. One can construct a double field theory version of it because little string theory enjoys T-duality as Vafa reviewed earlier this week. And then you can construct double gauge theory out of it, which actually combines nicely the usual vector field and self-dual two-form field. And so this is a gauge theory of the double gauge theory with the enlarged vector gauge symmetry. And this is a theory which does not have any gravity. And there you might anticipate that this is a nice framework or proxy of understanding how non-renormalizable Yang-Mills theory in higher dimension gets improved UV behavior as you march up toward the little string theory in 6 dimensions. So you might have some connection with the QCD string, as we heard in the morning by Kumargowski. And so so that's about, I'm lacking of time, so let me just stop here. Thank you.
Thank you. So we have time for one question. Well, yes.
How about the supersymmetric extension?
Oh, that's an excellent question. So in a supersymmetric case, in a heterotic case, there's a certain, depending on which sector you improve this double field theoretic the corrections, meaning which depending on which section you view, which sector the supersymmetric or non-supersymmetric as the dual coordinate version. The theory might have a tachyonic and ghost one, or non-tachyonic and massive state. So there are two different versions of it, and it has again improved UV behavior. The KLT kernel can be computed. What is mysterious is the fully supersymmetric type 2 double field theory. There you don't have any correction, and we know all we know so far is that type 2 supergravity has some unexpected cancellation higher loop order, and so double field theory does not really tell you much about beyond that.
Okay, thank you. Let's thank Soo Jong again.